Welcome to this explainer. If you're a student just starting out in computer science, it is so incredibly easy to get completely swallowed up by programming languages. You're trying to memorize the exact syntax, the brackets, the semicolons. It's a lot. But today, we're going to totally shift that mindset. I want you to start looking at programming not just as typing lines of code, but as actually engineering structural solutions. Think of yourself as a master builder. And algorithms? Well, those are your fundamental building blocks. They're literally the processing engines behind massive modern applications, AI training models, and huge big data queries. So today, we're opening up the Master Builder's Toolkit to explore some core algorithm design strategies.
But hey, to actually use our tools, we first need to understand what an algorithm really is, right? And honestly, it boils down to this one fundamental equation. Algorithm equals logic plus control. The logic part, that defines the meaning and the rules, basically what the algorithm is supposed to actually do. The control component is how that logic is applied. And here's the secret. By separating these two concerns, software engineers can optimize the control side for massive large-scale systems without ever having to rewrite the foundational logic.
Okay, let's dive into this. Here's the curriculum for our cognitive toolkit today. First, we've got the Master Builder Toolkit. Then, measuring efficiency with Big O. Strategy 1, divide and conquer. Strategy 2, dynamic programming. Strategy 3, greedy algorithms. And we'll wrap up with the ultimate limit, P versus NP.
All right, kicking things off with Section 1, the Master Builder Toolkit.
Now, before we actually start building, we absolutely have to understand our materials, specifically how our code actually lives and breathes in physical memory and hardware. Let's look at recursion versus iteration. Recursion uses these beautiful self-referential functions. It breaks problems down elegantly and expresses complex patterns with super clean code. But there's a catch. It is heavy on memory. Iteration, on the other hand, uses your standard sequential loops, for or while loops. It might look a little less elegant on the screen, but it is incredibly lightweight and highly execution safe. As a CS student, you really need to internalize that choosing how to implement your code is almost always a trade-off. You're constantly weighing the visual elegance of your code against the hardware safety of its execution.
Moving right along to Section 2, measuring efficiency with Big O. So, before we deploy these reliable systems, we need a way to measure the efficiency and complexity of our materials, right? We do this using Big O notation. Basically, Big O abstracts away all the quirks of different computer hardware to just show you pure scale limits. Taking a look at the major complexity classes here, O of 1 is constant time. That's a flat line, completely unaffected by how much data you throw at it. Moving down, we hit O of n, which is linear time. That's a steady one-to-one progression. But you really got to watch out for those bottom two. Quadratic time, or O of n squared, that curve shoots sharply upward, making it really only viable for small datasets. And exponential time, O of 2 to the power of n. Wow, that steepens so incredibly fast that it becomes completely unusable for anything at a large scale.
Now you might be wondering, okay, why do these abstract math classes actually matter in the real world? Well, consider this number, 10 billion. Let's say you just want to sort a dataset of 100,000 items. Pretty standard, right? If you use a quadratic, O of n squared algorithm like bubble sort, your poor computer has to perform roughly 10 billion baseline operations. But if you just swap that out for a linearithmic, O of n log n algorithm like merge sort, that massive 10 billion drops to just 1.7 million operations. I mean, that is quite literally the difference between a cloud system running flawlessly and a production server just completely crashing under its own weight.
Which brings us to Section 3, Strategy 1, divide and conquer.
All right, now that we know how to measure efficiency, let's bust out the first major tool in our structural toolkit. Divide and conquer is basically the ultimate organizer for deconstructing massive datasets. It's incredibly reliable because it follows a strict three-phase framework. Step 1, you divide. You literally split your massive main problem into smaller bite-sized pieces. Step 2, you conquer. You solve those smaller subproblems recursively until they're tiny enough to just solve directly. And finally, Step 3, you merge. You combine all those solved subproblems back together into one beautifully unified final solution.
Now, what's really interesting here is how straightforward the divide phase actually looks in practice. Looking at this Python code for merge sort, it simply finds the midpoint by chopping the list length right in half. Then, it slices the list into two halves and recursively calls merge sort on both of them. It just continuously shrinks those subproblem sizes down and down until it hits that base case of having just 1 or 0 elements.
Of course, once everything is broken down, we've got to put it back together. That's the merge phase. This little helper function uses pointers, you can see them labeled I and J in the code, to compare the elements of those newly sorted sublists. It grabs the smaller element first to keep everything in sorted order, and then just cleans up whatever is left over. By doing this recursively, it rebuilds the entire array perfectly sorted, guaranteeing that beautiful O of n log n time complexity we were raving about earlier.
Next up, Section 4, Strategy 2, Dynamic Programming. So if divide and conquer is our master organizer, think of dynamic programming as our ultimate memory saver. It's designed specifically to handle overlapping subproblems. In dynamic programming, we basically have two primary state caching strategies to stop our systems from needlessly recalculating things they've already solved. First, there's memoization. That's a top-down approach. It keeps that natural recursive flow we like, but uses lazy evaluation to cache computed states in a lookup table right when they're needed. On the flip side, we have tabulation, which is a bottoms-up approach. This uses eager evaluation and an iterative flow to build up a table from the ground up, completely bypassing any recursion overhead or call stack limits.
To really see why this matters, take a look at this naive recursive approach for calculating the Fibonacci sequence. The math is simple. F of n equals f of n minus 1 plus f of n minus 2. And yeah, the code is super clean and incredibly easy to read, but man, it lacks memory. Because it doesn't remember any of its past calculations, it branches out wildly, recalculating those exact same smaller Fibonacci numbers over and over again. All that redundant, repetitive work creates an exponential O of 2 to the n time complexity, which means it will literally freeze up your machine if you try to calculate larger values.
And this brilliantly illustrates the real power of dynamic programming. By simply adding a lookup parameter, basically a little cache to store values we've already figured out, everything changes. Before the code makes any new recursive call, it just peeks at the lookup table. If the answer is already sitting right there, it just returns it. No extra math required. That one tiny addition drops our time complexity from an unscalable exponential nightmare down to a super sleek, highly efficient linear, O of n time.
Or, if we want to just ditch the recursion entirely, we can use tabulation. Check out how this iterative code handles it. It just initializes an array with our base cases of 1 and 1, and then iteratively loops forward, adding the last two results together to get the next one. It's so straightforward. This completely sidesteps any of the call stack limits you get with recursion, acting as the absolute ultimate optimization for state management.
All right, Section 5, Strategy 3, Greedy Algorithms.
Now, the greedy algorithm is our fast, local optimizer tool. But listen, as a master builder, you absolutely must understand its exact limitations before you just deploy it in the wild. A greedy algorithm approaches a problem sequentially. It makes the immediate, absolute best possible local decision at every single step, with zero backtracking, no second guessing. Let's look at this coin counting example. Say your goal is to make 12 using the fewest coins possible, and your denominations are 8, 5, and 1. The greedy approach? It sees that 8 and immediately snatches it, because it's the biggest. That leaves 4, so it just grabs 4 ones. Total coins used, 5. But wait, the truly optimal choice is taking 2 5s and 2 1s, which only takes 4 coins. The greedy algorithm totally failed here, because picking that 8 right out of the gate trapped it in a local optimization, entirely closing off the path to the best global outcome.
When you look at a basic greedy Python implementation for making change, you can instantly see why it's so incredibly tempting to use. I mean, it's blazing fast, it's super simple to write, and it iterates cleanly from the largest coin down to the smallest using standard integer division. And honestly, it works flawlessly for standard US or European coin systems. But because it completely lacks the hindsight to backtrack and rethink its choices, it falls flat on its face in custom, complex problem spaces where taking the biggest piece right now isn't actually the smartest long-term move.
And finally, Section 6, the ultimate limit, P versus NP.
Okay, we are going to zoom way out now. Let's step back from our specific coding tools and look at the absolute horizon of computer science, exploring the universal boundaries of what we can actually compute. In CS, we categorize problems by how ridiculously difficult they are to solve. Class P problems are what we call tractable. They are easy and fast to solve on actual hardware, like simply sorting a list. But Class NP problems, they are an entirely different beast. They are exponentially, mind-bendingly hard to solve from scratch. But, and here is the kicker, they are incredibly easy to check once someone hands you a proposed solution. Think about integer factoring.
Finding the prime factors of some massive 250-digit number could take a supercomputer millions of years. But if I just hand you the proposed factors, checking if I'm right takes a fraction of a second. You literally just multiply them together.
And that brings us to one of the most famous unsolved questions in the world, the Millennium Prize problem. It actually carries a cool $1 million reward. It asks simply, does P equal NP? Meaning, if a problem's solution is really easy to check, is there some secret hidden way to also find that solution easily from scratch? Now, why does this matter for you, the student? Because a huge chunk of big data and AI training problems are actually NP hard. Understanding these theoretical limits prevents engineers from wasting years of their lives trying to write a perfect exact algorithm for an impossible NP problem, when they really should be writing a fast, approximate algorithm instead.
I want to wrap up this explainer by leaving you with a bit of a provocative thought. Modern cryptography, the actual underlying math that secures RSA encryption, digital banking, and the entire blockchain, relies 100% on the assumption that class P does not equal class NP. It assumes that while a password is super easy to check, it is practically impossible to just guess from scratch. So, think about this. If someone actually proves P equals NP tomorrow, providing a blazing fast way to solve those impossibly hard problems, how does that affect the entire modern digital world? It's a pretty wild reminder that the theoretical algorithm strategies you're learning today are the exact same principles securing or potentially breaking the technology of tomorrow. So keep building and definitely keep questioning.